Welcome to the fourth week of the QuantUniversity Summer School 2020. So this summer, we are doing the whole summer school online, and we are pleased to invite Dr. Agus Sargento from Wells Fargo, and he's going to be speaking about model risk and machine learning, two really cool topics and two of my favorite topics. And Agus is one of the experts in the field, and he has been able to take the whole aspect about machine learning and model risk management and has brought all the core issues to the forefront. And he is a practitioner, but he's also very much involved with research and also is an active contributor to the research community by writing papers. So I'm very pleased to invite Agus. Thank you so much, Agus, for joining today's QuantUniversity session. And I'm going to make a couple of quick announcements for people who are new to the QuantUniversity community. And I'm going to introduce you to a couple of different things we are doing. And then I will hand it over to Agus. QuantUniversity is an analytics advisory, and we are based out of Boston. And we started out QuantUniversity in 2013 to look at the intersection of quantitative finance, machine learning, and data science. We were seeing this whole confluence of new technologies come into play, and we wanted to make sure that we were in the forefront of all the core things which are happening, but also from an advocacy perspective, from an education perspective, we were there to provide guidance and also provide our insights and expertise in terms of helping companies implement these technologies. We had more than 1,000 students take our courses through various channels, and we have been offering courses through the Q Academy. And we have a bunch of certificate courses. And this summer, we are offering a specialization in model risk management and machine learning. So as part of the summer school, we are offering these three classes, one primarily focused on Python for data science, an introductory class. We call it the Explore series for people who are really new to machine learning and data science, machine learning and AI, a financial professionals course. And this course is primarily geared towards people who are in the financial services domain and who are interested in understanding machine learning and artificial intelligence. And the third course is primarily geared towards model risk professionals, and it's called Model Risk Management for primarily machine learning models. So we have people from more than 12 different countries take these classes, and we have regulators, we have consulting companies, we have banks, we have asset management companies. So we have a whole diverse group of professionals taking these classes, and we are very fortunate to engage with them and offer these courses. In addition to that, we have a weekly speaker series, and this is the third week, and we are going to be spending the next hour talking to, Agus is going to be talking about model risk and machine learning, and we have many other programs coming up. In the next week, we have Dr. Julia Fanti from Carnegie Mellon University, and she's going to be sharing her research on generating synthetic data using GANs, or generative adversarial networks. So without further ado, I would like to introduce Agus Sargento. The agenda for today, we're going to hear Agus's views and his presentation for the next 35-40 minutes or so. And then we're going to have a virtual fireside chat and Q&A. It's too early to have a fireside chat, but I did get my hot cocoa with me so that we can enjoy the conversation. And for people who don't know Agus is the Executive Vice President and Head of Corporate Model Risk at Wells Fargo, and he's responsible for enterprise model risk management. Prior to that, he was at Lloyd's, and we were just having a conversation about London. And prior to that, he was also at Bank of America. And Agus holds various US patents, both in finance and engineering. I don't know how you do it, Agus. It's such this fantastic combination of engineering, finance, and he's the co-author of Design and Modeling of Computer Experiments, and he has expertise in credit risk modeling, machine learning, and computational statistics. And now I know, you have advanced degrees from Wayne State University and also from Massachusetts Institute of Technology, which is like 15 miles away if I drive east towards Boston. So I wish I knew you when you were, your studies, so I could get some advice from you at that point. Without further ado, I would like to hand over the baton to Agus. So let me just stop sharing, and I'm going to make you the host, Agus.
All right. Thank you. Let me thank you, Sri. Thank you for the kind introduction. And I would like to welcome everybody here, spending the next hours with me here to discuss the topic that near and dear my heart. So we'll talk about machine learning and model race today, and I will focus a lot more on the explainability and robustness, and particularly the neural network. We go to more in depth in that because that's how to make my view that neural network is the most interpretable model in the machine learning world, and we'll talk about that how we do it. And so I'm going to go through my presentation probably, hopefully, in about for about 35 minutes, so that we can have about 15-20 minutes at the end for Q&A. Okay. So let me start with where I came from. I work for Wells Fargo. I'm the chief model race for Wells Fargo, and sharing with you that bank runs by model. So we use model for both financial model. That's a traditional area: credit, market, liquidity, revenue, loss, stress test, capital management, investment. So those are the whole gamut of financial model that traditionally bank always use, and bank use them a lot. But bank also use a lot of non-financial model. This is where the a lot more machine learning applied in this area, dealing with the customer service, financial crime detection, marketing, compliance, staffing, you name it. So we have the whole gamut from something very mundane to something very, very sophisticated. And I give an example. For example, when you make a phone call to a bank, to the call center, and you call because you lost your credit card or you left your credit card somewhere and you need to get the replacement. And those your call will be monitored by bank's machine learning model, and will get evaluated in terms of where the call's coming from, the what line do you use, what phone do you use, the voice biometric, the background noise, etc. And decisions are made by machine learning to advise the person that answer your call to what to do. In particular, if the call can be fraudulent, the model will say it as well. So from something like that to all the way in the current situation during the COVID-19, we have to perform stress tests. How is bank going to survive in have enough capital under more severe scenario that we have? So that's what the whole gamut, and of that. And every model in banks has to be governed appropriately, have to be tested appropriately. So the use of model for a financial institution create both financial and non-financial risk, and they are heavily regulated through the life cycle of model by regulatory guidance called SR 11.7 in the US. That's by the Fed, or the sister of that called OCC 11-12. It's really governing end-to-end life cycle for all model, require independent model validation, require monitoring and mitigation. So some of you that interested in that not familiar with SR 11.7, you can follow the link there that I have. Now, in terms of machine learning, uh, we banks apply machine learning for various area, the area that traditionally the domain of statistical model, like credit risk and financial crime. So in there, typically people apply both supervised and unsupervised machine learning. In financial crime, you do outlier detection. That's unsupervised machine learning. Uh, Banks also use it uh, as an alternative to statistical techniques or as a model benchmark. You compare the model production probably is a standard statistical model, but it's benchmarked the performance with the machine learning model. Or machine learning model are used to diagnose, to do feature engineering, to do variable selection. So in the whole thing, some model really machine learning get implemented or used as a benchmark or used as a tool to do feature engineering for more traditional models. So the whole way, various way model used to as an alternative to a statistical model. We talk about the non-financial risks. Banks also use for area that previously no model, like in compliance, conduct, customer assistance. So monitoring traders' behavior, looking at their chat and their email conversation. Those are done through machine learning, through a lot of NLP application in that. Having a assisting customer when customer complain, where's the complaint need to get routed to? That's a machine learning model through that routing the complaint, and many other area that you're familiar with, like chatbot and all of those things. Other area that banks, commercial bank like Wells Fargo use, we use it for alternative techniques to do intensive numerical computation. This is the domain of derivative pricing and market risk, where we apply deep learning for stochastic PDE solver, or we use GAN to model stochastic process and time series for simulation. So we can. There are several paper that I gave here on the in the link that how we use it as an alternative for derivative pricing. So if some of you that interested in, you can follow the links and look at the paper and archive. Those are some of works that my teams are doing and publish in archive. Let me start with this before I talk deeper in terms of the model and how to do things. Let's start with model risk. So this is from the famous George Box. All models are wrong, some are useful. That's what George Box said. I would say somewhat differently. I would say all models are wrong, and when they are wrong, they create harm or damage to financial institution or to customer. So that's what really where we start with when we're talking about model risk. All models are wrong, and when they are wrong, they produce damage to the company or to the customer. And that can be both financial harm or non-financial harm. Financial harm, you lost money. In the non-financial harm is reputation, compliance, or legal. So I give an example. If the model is for hedging, then model create market risk because it's mishedging. For financial crime or conduct surveillance, when model is wrong, it misdetection. So this create compliance risk. So if for money laundering, then you miss detection. Staffing model, when model wrong, it can be understaffed. Customer has to wait for a long time. That create reputational risk. Credit approval, when you sometimes model risk is nothing to do with the purpose or the performance of model. For example, on credit approval, yes, we want to choose customers so to be able to force rank customer in terms of credit worthiness, but it can create model risk too in terms of fair lending if the model make a discriminatory decision for protected class. So that's create fair lending and compliance risk. Online marketing, this is something that sounds very, very innocent. So when you go online, you get product offering. You in social media like Facebook or Instagram, you got all those advertisement, right? Similarly, when you go to bank, you go to your online system, you will get product offering. So the goal of the model is to create product offer that will be reviewed or will be received by customer, right? Looking at the propensity, but that's the model performance. But in terms of model risk, it can be completely unrelated to that or somewhat unrelated. For example, when you do product offering, they will be based on the cookies, based on the website that was reviewed before, was visited, and all of those things. And web usage, cookie usage, we're dealing with privacy. And it's can be very demographic as well, the way people use behavior in the online. So it can create a fairness issue in terms of product offering that create legal risk. So this is just a few illustration that all model are wrong, and then when they're wrong, they will create damage to both the institution or the customer. Let's look at focus a little bit more on the model risk, and when we talk about model validation. This is my view when we look at model validation for the purpose of model risk. A lot of people thinking about model validation is looking at the model performance, how performance can be improved, etc. It's important aspect to look at model performance, but from model risk point of view, we cannot just look at model performance. We need to really question how model will fail. What's the model risk? Then when model wrong, you create damage, right? So it's very important to have the acceptance matrix. What is how wrong can a model will be? What is the acceptance criteria? I give an example, very simple example that many of you are familiar. Let's say false negative. If misdetection, if for financial crime, misdetection is very important, then we look at what kind of misdetection are sufficient and how much misdetection is acceptable, and why is it acceptable. So acceptance criteria matrix in terms of model risk, very important. Then from the definition of model risk, what the model can go wrong, how are we going to measure it? We start asking questions to do root cause analysis. What are the root cause of the failure or harm? It can be from data, it can be from other input, it can be from modeling framework, it can be from variable selection, it can be from training, parameter estimation, hyperparameter tuning. It can be from implementation or misuse. So understanding the root cause, very important, so that we can say, okay, that's a potential root cause. Let me create a test to failure. This is a very fundamental concept in model validation. Not only testing for performance, but test model to fail. When I was an engineer, I used to be an engineer at Ford Motor Company. I used to be one of the engineering manager that leading the design of a V6 and V8 engine at Ford Motor Company. So we always test product for failure. If you have your iPhone must be tested in many ways to look at how can it fail, including something that, let's do a simple thing like a drop test. How much height I can drop my iPhone so that it won't be broken, right? No product failure. So when dealing with model, it's very important to test for robustness or adversarial test to identify model failure, how the model will fail, how much the model will fail. And then from that, quantify the impact for each root cause, because it can fail because of data, it can because of training data, it can fail because of the features. So how much is the impact of that root cause to the acceptance matrix? And then from that, understanding model weakness, understanding model failure, we put a mitigation, a monitoring, and how to manage the potential harm that model are created. For machine learning in specific, for machine learning a bit more specific here, there are common causes that model risk. One is many of you are aware, and a lot of exposure in the press as well, about data defect and bias. Input, both in the input and target training data, because bias can be coming from input, bias can be coming from when you label the data. Beware of implicit bias. This is very important because it can touch the ethics issue. If the bias, this is sometimes a difficult decision that you have to make. do you want to build this model for this particular application? If we're dealing with societal bias that's implicit in the culture in the society, you have to be willing to say, no, we're not going to do this. So in other area, you can probably do some treatment on the data to reduce the bias. But sometimes in many situations when we are working on this, we probably facing with the ethical issue and the societal bias that we just say, no, we're not going to build model or apply model for certain application. Conceptual soundness is very, very important in the machine learning world, particularly because we're dealing with a lot of variable. We will be dealing with spurious variable effect, confounding factor. We're going to talk a little bit deeper on the conceptual soundness and how we deal with conceptual soundness. And this is where the area of machine learning explainability is very, very important. So we're going to delve in more detail in terms of machine learning explainability and how to build machine learning model that is interpretable from the ground up. So we'll spend a lot of time today on that subject. Model robustness, I talk about that, touch a little bit on this. The machine learning community is the obsession with model performance. For example, like in Kaggle, you can have a third digit improvement and your rating will be up. The obsession with automatic machine learning, AutoML, to choose model that has the best performance, hyperparameter tuning, or data mining on the feature to get the best performance. I'm not saying that performance is not important. Yes, performance is important, but we have to understand real world is dynamic, data driven. So if you choose model which have the best performance, it may not be in the real world perform the best because the world changed. So we'll talk about model robustness in a bit detail later. Model change control, I'm going to touch a little bit of this. It's important because machine learning model is highly non-parametrics. It can fit anything. So if the data change, you retrain it, basically you change your model. So change control is extremely critical. When you do that, you have to go back to look at, do I have bias, introducing bias? Do I have conceptual soundness? I need to check for model robustness again, because retraining produce a new model. Model use control, because we know model will fail. When they fail, it need to fail. Is it acceptable? Some area is zero tolerance in terms of failure. Others, when dealing with compliance in financial institution, other are really more soft failure that we can fail graciously or in an acceptable way. All right, let's talk about conceptual soundness a little bit. This is critical to have a trusted model. We need to understand when we have machine learning model, does the model make sense? Can we trust the model? How's in the context of model risk, how's the model going to fail? We need to understand it. With this, model explainability is very, very important to understand whether model makes sense or not. Is the features that are being used as an input and critical feature makes sense and their effects make sense. So when we're dealing with machine learning, outcome testing alone is not enough, because we typically split data from testing, training, and testing. Often in the testing data, we split it further for validation to choose hyperparameter. So testing input and output, pick the best model alone is not enough, because we need to be able to understand, to explain if the model really makes sense, processing input, and it's the right input, the feature makes sense, and the relationship between input and output makes sense, the attribution because especially in when it comes to model that make impacting our customer, for example, approving credit or not approving credit, increasing the or decreasing the line of credit, or any other impact to customer, we need to have a attribution to understand what are the adverse impact to customer. And of course, also to understand failure operating region, area where model will be the weakest. It has uncertainty, so that the model can make a cautious generalization. How do we do this? I am going to focus on one area. So a lot of techniques in the input-output explainability. This is also known as post hoc analysis to understand input and output. A lot of techniques in there. I'm going to touch very briefly. Not going to spend too much time on that. That's becoming more standard today. Model distillation, basically second approach is through model distillation. Simplified creating a simplified and interpretable model to explain the more complicated machine learning model. And the third approach is structured interpretable model. Let's build a machine learning model that is explainable, interpretable from the ground up by constraining the model structure or model architecture. And this we can do a lot with neural network on this. So I'm going to spend more time on the third subject. Before we do that, I'm just touching very quickly on the post hoc attribution, the first input-output explainability. A lot of techniques out there: global variable importance, sharp, PDP, and all the whole gamut of explainability techniques that I'm assuming Sri is covering that in his course. And a lot of textbook, a lot of now start getting more popular, incorporated in many software have the explainability tool. So I'm not going to dwell too much on that one. Model distillation basically is many different techniques as well. So one of the most popular techniques is basically using tree. And in this example, we use a tree, and at the node, instead of just constant, it has a regression equation. So I'm doing a regression with tree at the terminal nodes, and because this is at the terminal node a linear regression, the becoming a very interpretable, because you can see all the coefficient like in that. So some of you that are interested in can go to paper that we published in arXiv. I'm going to talk about more how to build interpretable model from the ground up. I would like to argue that neural network, we can make neural network as the most interpretable machine learning model. That's what we're going to do here. So linear model, everybody know linear model, very standard regression model. And then how linear model, how regression dealing with nonlinearity, introducing spline. Basically, the simplest thing is instead of just X, I'm creating a basis function called B here. And the simplest basis function is basically piecewise linear. Above certain threshold are linear, or certain region are linear, then that will be zero. So we have a summation of piecewise linear model. Now, of course, people can use higher order polynomial, but let's do for time being very simple piecewise linear model. Then you can have piecewise linear model, then becoming you have nonlinear model. And that's what spline is in statistics, basically, right? The traditional statistics, non-parametric statistics, introducing spline. And special case of spline, for that, when we're dealing with higher dimension, we call what in statistician called single index model. Basically, you project it first into univariate variable. You project it, you multiply it by a vector to make it univariate, then you apply spline on that univariate, so you have what we call it single index model. It's called single index model because the variable from high dimension, it's reduced into single dimension D index, and then you apply spline. So this In neural network, it's a very, very straight. If I do spline, I can do with this univariate. I do piecewise linear. Neural network people call it ReLU, right? This is the ReLU basis function. It's the same thing. So neural network and spline in a univariate is the same thing. So in single hidden layer network, it's basically single index model. I'm going to generalize it now. Instead of single projection, I am going to get many, many, many projection. If I do many projection, no longer single index, but becoming multi-index, right? So that's single hidden layer network. Single index model is very, very interpretable because I can see the regression, what is the impact, and then univariate, and I can plot it, what the effect of that, right? So single hidden layer network, it's also can be seen as, especially if it's piecewise linear, we'll talk about that a little bit later. If it's piecewise linear, basically it's a summation of piecewise linear model. So it's a linear model. If a single hidden layer network with ReLU basis function locally is a linear model, globally is nonlinear. The locally, we can see exactly what variables are important, so we can see the interpretability are very, very clear. How do we deal with if we want to be more sophisticated, right? This is what we call it additive index model. So instead of fully connected network, now I'm limiting my input only very, very few projection. And after I project it, instead of applying spline, I can apply deep network as the nonlinearity and then combine them at the end. This is additive index model, neural network implementation of additive index model. If we're dealing with small number of projection, we can see all the regression coefficients. So we can see each subnetwork is doing something. I have a linear equation. The beta can be have clear interpretation, and then univariate, I can see what the nonlinearity is and then how it's combined. So additive index model, we can use that as an explainable neural network. You can implement in a neural network by limiting the number of input projection to make it a lot more interpretable model. So some of you that are interested in can follow the more detail in the archive paper as well. This is an example of that. So let's say I have this network is using 4 modules. If you go to the previous slide, I have 1, 2, 3, 4 modules, and each module you can see the projection, this variable that's in there, another variable, so you can see very, very clearly, and you can see the nonlinearity from each module as well. So you can have model that's very, very interpretable. That's the whole idea behind explainable neural network. We can make it adaptive. So some of you that are interested in, you can look at the paper in archive as well. What this one is, okay, let me make it even more interpretable. Working on explainable neural network that make it even more interpretable. So the techniques is, I'm going to do 2 stages. Stage 1, I'm going to be main effect only. So I'm creating like generalized additive model, GAM, right? Because it's univariate, I have GAM. A single factor, so you can see what's nonlinearity. After you exhausted main effect only, then you apply X and N in previous page to capture the interaction, so you can see what interaction coming after that. So it's becoming very, very interpretable because you have the main effect for important variable, and then you can see the interaction effect. So again, some of you that are interested in more detail, you can follow in the archive paper on that. How about fully connected network? When we're dealing with fully connected network, deep network with ReLU activation function can be decomposed into local linear model. Deep learning and with ReLU, at the end of the day, is additive index, additive piecewise linear model. So ReLU, deep network with ReLU locally is a linear model, and you can extract local model for each of the point and the prediction, so you can get local exact interpretation. Let me go back a little bit. Because every deep network is local linear, you can flatten deep network. After the deep network get trained, you can flatten it into single layer. We're going to publish this paper probably in 3 weeks. You will see it in archive, how to flatten deep network into single network. So deep learning, you can flatten it into a single layer network. So the equation becoming like this, right? Just becoming very, very wide. So after you train deep learning, you can flatten it into single layer, flat, large network, then you can prune it. So the when you have a single layer, you know it's a piecewise linear, and you know exactly the coefficient, and you know how it's being combined. So that's the key in the deep ReLU network. Local interpretation is exact. You don't need SHAP. You don't need any post hoc. You don't need any of those variable importance, all the strict. You don't need Lime to understand it. You have exact equation for a deep ReLU network. Uh, so you can see it in this example, basically. So locally, you can see what is the effect of each variable. And some of you that work in banking, if you need to have recent code, why credit is being declined, you can see it why it's being declined, because those variable importance. So recent code can come out very exact in a deep ReLU network. How about if globally? How can we understand globally? Globally is very, very simple too. Calculate locally every sample point, calculate locally. That local coefficient is basically in the language of calculus is dy dxi, is partial derivative. Then you can plot and you can average them, you can plot. In this example, the x variable, and on the y here is dy dxi, the partial derivative. So in this column here is dy dx1 again x1. When I change x1, how the gradient toward with respect to x1 change. If it's constant, meaning the model is linear, right? The gradient is constant, is linear. Here is the effect. When it's changing here, x2, then you can see it's non-linear because it's constantly changing and changing constant and monotonic. So it's a monotonic. It's you can see this one as that. And this is second derivative. This is the derivative. It can be non-monotonic. You can see it. So the diagonal here is the main effect. And then the off diagonal in this one example, dy dx3 against x5, partial derivative on variable compared to the other. This is the interaction. Interaction within variable 3 and variable 5. You can see when they are not constant, they have strong interaction. So globally, you can interpret it in a very, very exact way as well, because you have local linear model. So that's in terms of explainability, and we can make deep learning as the most interpretable model. It's not, I cannot say the same thing for other ensemble model. Other ensemble model like boosting and random forest naturally is much less interpretable. So you have to use a different technique, the explainability techniques. I like to use deep learning because you can, from the ground up, you can make a very interpretable model. So if people out there talk about deep learning is not interpretable, it's the most black box, that's actually is the opposite. Deep learning neural network is supposed to be the most interpretable model. Here's another a topic that I want to cover before we open it up for Q&A. This is a very important one. Model robustness test. This is core and center in managing model risk. Building real world model, as I said, is not Kaggle competition. Uh, it's not talking about third digit improvement or even second digit improvement kind of things that we're talking about. Current AutoML miss important aspect of reliability of model. Too much focus on model performance and do not address model robustness. That I talk about dynamic environment. When we build model, I split the data into training and testing. When we do training and testing, you assume your data is static. Your data doesn't change. In real world, data change. So this is how we want to make sure that we design model that's robust against environmental changes. I remember in my engineering day when I designed engine will operate in a different altitude, different temperature, different humidity, and the performance has to be very consistent. So the same thing for model. Model will be exposed to different kind of population drift, and model need to be more robust. So in for natural language processing, for example, you need a robust model because model that's not robust, it will very susceptible to adversarial attack. People change the word a little bit, or change the with synonym, or even change the character. The model can misclassify. So it's very, very dangerous to just looking at performance based off static testing and training data. We need to test for model robustness. We need to test for adversarial attack. So this is an example of, I just gave a small illustration here. I have model. If I just split it based on training and testing, this two model has the same performance in terms of accuracy. Yeah. But then when I perturb the input, one model more robust, the performance. This is the size of perturbation here. The size of perturbation. The models, they're performing very well. The one in blue, the one in in yellow here perform degrading very, very rapidly. So clearly this is not model not robust here. So this is something that we need to pay attention. You choose model that's blue, not just model that is in amber here. This is another example. If we choose solely based on testing and training data, I will choose the blue model here because my MSE, I'm sorry, the amber here, because my MSE is smaller. So you run AutoML, you choose the one model that the best, you choose this model. But when you perturb the input, the model degrades very, very rapidly. While this model, even though the performance in terms of MSE is bigger, but it's very robust, when you perturb, its performance doesn't degrade as much. So very, very important here, because model will be, NLP model will go through adversarial attack, right? Other model will experience population drift. How to deal with this? Let me close my talk so that we can have 15 minutes for fire chat or Q&A here. Governing machine learning model risk here. I'm sharing a little bit about what we do in Wells Fargo. We have policy and procedure governing model life cycle. This is the from inception of model to retirement of model. We have our enterprise innovation team that focus on AI strategy and our coordination across the company. So we have a deployment and development that's more coordinated across the company. We have what we call it Model Development Center of Excellence. We have centralized model development, including all vendor model has to go through Model Development Center of Excellence to be tested in terms of model risks corresponding to what we discussed before. We have dedicated development and deployment platform that we use. We have model validation standard. We have a dedicated team that focus on machine learning model validation. standardized library and tests. I share with you a little bit in terms of explainability, in terms of the a lot of fairness testing, robustness testing, that the model library that use to test machine learning that we have. And I spoke a little bit about the non-financial risk, reputational risk, legal risk when we apply machine learning. So legal and compliance partner are very, very critical for us to review and to provide their approval. So with that, Sri, I think I'm hitting. We have 14 minutes probably to open Q&A, Sri.
Oh, thank you so much, August. This was an absolute pleasure. I learned a lot myself too. I was kind of recollecting my days as a design engineer. So you were manufacturing cars in Ford, and I was manufacturing hydraulic excavators for Komatsu back home.
Yeah.
Kind of the fun days when we were, dealing with these really large steel plates and doing fatigue testing to figure out when these plates would fail before we can deploy them. And my first job was always the best one because I was sent to this field with 25 other hydraulic excavators, and we were basically taking all the mud and throwing it apart, and it was a blast. I mean, kind of wish I could go back to those days. So we have a couple of questions. I think a couple of them are very specific, so I think we'll get them out of the way. I think the one specific one was in the prior chart. What was the x-axis, which was the R, was one of the questions.
Very good. R is the size of perturbation. Okay. So you define, and this is, I put it in more general term here. R is the size of perturbation, and D, how you define your perturbation, because so many ways to do perturbation. As simple as the simplest things, you do random perturbation, right? That's the simplest thing. How big is your random perturbation, basically? It can be more sophisticated. For example, my perturbation is defined by the covariance matrix, by the eigenvector. You perturb the eigenvector instead of perturbing the one variable at a time. So there are many ways here to define what do we mean by perturbation. Because, for example, this is very important. When we apply machine learning, we apply to very heterogeneous data. That's why in machine learning, typically, we don't do segmentation. In traditional modeling, we do segment the data, and for each segment, we build separate model, right? That's what we do. In machine learning, typically, we don't do segmentation. We model the whole thing together. Now, because we don't segment it, each segment, they are different. Their correlation, their covariance matrix will be different. So, and we know population drift. Today, probably we originate 70% of customer A, 30% customer B. In the future, it may flip. So we have to perturb it with the covariance matrix or the structure of the of each segment. So there are many ways how you define D. I'm just but in the end, R is really how the deviation from the original training data.
Cool. So I actually had a question about how do you manage drift in your models? Do you have any specific measurement metrics, or is there a process involved in terms of understanding when these models fail?
Yeah. The traditional approach is one variable at a time, right? That's called population drift. PSI, right? That's the more modern one is multivariate way, right? To detect that, and many different ways you can do it, including if you want to do auto encoding, right? If you have auto encoding, you use auto encoding, then you can look at the error, right? The error reconstruction. If you have drift, your error reconstruction will be bigger. So you can do it multivariate. If you want to use machine learning, then you do auto encoding to do that. So that's really more on the population drift detection. You want to do univariate, or you want to do multivariate. But I'm talking in here is upfront during model development, during testing. Can we test it for robustness, right? Just like the way we do in engineering, right? We sub-test it under different environment using the training and testing data that we have.
Absolutely. I think there's one more question with respect to the to the deep neural networks and the interpretation aspects of it. I think the question is, in terms of taking the model and looking at the piecewise linear aspects of it, isn't it the same as taking any neural network, approximating it locally with the linear model, and then looking at the coefficients is the question.
Right. You don't need to approximate it locally because it's exact in neural network. You don't need local linear approximation. You don't need line. It's exact. If you use ReLU, it's exact. Unless you use tangent hyperbolics or sigmoid activation function, you can do then you need to do linear approximation. But today, I don't honestly. Yes, you can get something more smoothness with tangent hyperbolics with ReLU, but why do you want to do that complication? Why not just use ReLU when piecewise linear is good enough, and locally you get exact interpretation. You don't need local linear approximation.
Right. And it was one of the questions I always had is, I look at your LinkedIn profile and you always have hiring STEM PhDs.
Yeah.
So it seems like you have a very robust, no pun intended, team to help you build all these machine learning models. But many times when we go in, we kind of see that a lot of companies have the skill gap. They have a very strong, core machine learning development team. But when it comes down to the model risk management team, they're not that sophisticated in terms of understanding all the mathematics and the models, but they are tasked to validate these models.
Yeah.
So how do you kind of balance out this disparity in terms of both skill sets, which is real, but also the expectations from different groups?
Yeah. Well, we always hire. We do hiring, and every year we hire about 50 fresh PhDs. Right. That's what we do. Fresh out of school with zero experience. We train people through a job rotation for 1 year in model development and model validation and permanent placement. By the way, we don't only hire PhDs. We hire PhD and master level. The only thing we hire PhDs is because of the for visa issue, visa sponsorship. So it's easier to get visa approval for PhD. But we hire master as well. In the model validation team, about 90% are PhD, 10% are masters. In model development, it's the population of PhD is much smaller. It's about 40% PhD, 60% masters in model development. So why we do that way? Because in model validation, the job of people in model validation is to break model. So to break model, you need to be more sophisticated than the model or the other side that you try to break, So it's just like you have to be a smarter hacker than what you want to hack, right? So that's at the end of the day what we do, why we staff a little bit more tilted to PhD in model validation. But we hire very, very broadly.
And another question, which is more of a process-related question. I think there are a lot of moving pieces, as you can understand. Oh, by the way, just to kind of, you had alluded to all these metrics. So I'm going to see if we can do a quick demo at the end. But we have these coming up in the next module, wherein we are basically, building out a bunch of demos to illustrate how you can do assessment of fairness and assessment of explainability and various ratios and concepts. So that's all a part of the course for people who are taking the course. The process piece is, again, interesting. I've been tracking the evolution of all these tools, especially coming out of the Silicon Valley. You have tools specifically for model management, specifically for interpretability, specifically for, provenance-related issues, and you have privacy-related tools. So how much of your ecosystem is built upon, cobbling up all the open source tools and then building out a workflow versus you adopting these people already have these systems in place. Let's just adopt them and incorporate them into your work.
Right. We have mixed a lot of things that we do, a lot of open source and internal development. So model validation, because they have to be independent in heavily regulated industry. So we tend to have model validation system and testing library that they build internally. Model developer is tasked with fast turnaround, right? Quick turnaround, build model. So they will look at productivity tool, whatever available out there, combined with internally developed. And then, of course, the model deployment as well, because explainability and monitoring is not only for model development, but also for model monitoring because model change. So people that is in production model monitoring is less technical people. They don't have PhD and they need to maintain production. So they need automated tool, nice, readily available tool that do that. So model developer, they have mixed combination, to from tool that's available out there as well as internally developed. So it vary. Model validator tend to be custom built. They want to do the best, the latest, because that's their job to really break finding what's wrong in the current one. And the production people and the model developer tend to use a tool that's available out there combined with internal enhancement.
Interesting, very interesting. I think there's a follow-on question. It's about benchmarking of models. So do you benchmark one machine learning model with another machine learning model? How do you kind of look at it, and
Of
any
course.
guidelines from SR 11.7 you follow, or
Yeah.
just a process-related question?
Yeah, I think the important on benchmarking is this. We do benchmarking not only model performance. Yeah, this is very key. Model developer, they need to benchmark for model performance. They pick the model that best performs. In model validation, model risk, focus on benchmarking to look at model risk. How wrong model can be. Which one, when it's wrong, has less damage, right? So I give you example in my slide, in slide 16. We do benchmarking, compare model A and model B. Which one is more robust? If I perturb the input, how is the classification going to get flipped? Which one has more error? So for model validation purpose, for model risk purpose, you need to have model validation, model benchmark, particularly to see how much model risk that one and the other create in the non-ideal situation, basically. So that's what I try to advocate here, because it's very important. Model benchmarking also important to say, I am going to build machine learning and all those things. At the end of the day, if we talk about neural networks, for example, at the end of the day, the final layer of neural network is GLM, right? It's GLM. Before it is all feature engineering, right? Transforming into embedding space that linear model will work, right? I give an example, singularity network, the last layer, it's just linear model. Deep network, we can flatten it into single layer network. So it's very, very important. Even if you want to implement it as a GLM, you can look at it as the features, what feature that is the best. So benchmarking important either for performance, robustness, or for feature creation.
Absolutely. And do you use traditional stress testing, back testing, and do you have a process around, like, well, when you submit the model to the model risk management team, you should have done these, this level of testing.
Of course, those are the standard stuff, right? Best testing you have to do, and part of robustness is basically how robust the model is. If the model is stress testing is part of that, I'm going to subject the model into different scenario, right? How do you perturb? You do sensitivity analysis is part of that as well. So yes, you do a lot of stress testing is a must. And if models, then the question is, how do you do stress testing? Is stress testing you based on the external environment, in some model is macroeconomics, or it's really more the internal, endogenous effect, the loan level type of characteristic or something?
Interesting. So just to kind of give a plug about that, we are kind of evaluating potentially using synthetic data as a way of augmenting your traditional use cases for stress testing. And in the next talk, Dr. Julia Fanti is going to be sharing some of her work on building upon GANs, and she's going to be speaking about synthetic data generation from a time series perspective. So we're kind of looking at the whole area of, if you do not
Yeah,
have
yeah.
enough data and enough test cases, how do you think about it?
Right.
Do you have any
By
views?
the way, if some of you interested in GAN, some of example of our GAN paper, you can also go to archive.org and search under my last name. It has GAN paper there that talk about how you scan for macroeconomic, large-scale macroeconomic modeling, as well for value at risk simulation.
Absolutely. And I was kind of looking at one of the papers. Do you just use the univariate approach, or is that a multivariate approach?
Multivariate approach.
Okay.
Multivariate approach. If you look at the paper in the archive, is for macroeconomics, especially factor autoregression model, right? For VAR, we do it for high dimensional VAR,
Okay.
So 500 dimension, if equity basket, how do we simulate 500 time series simultaneously?
Very interesting. And as I was mentioning to you, Agos, I think one of the goals of these series of talks is to put together a white paper at the end of the summer school, incorporating views from various practitioners, views from various academics, and putting together a paper which basically talks about like the challenges, the opportunities, the state of the art, what we are saying, primarily coming from a practitioner's perspective. So I'd love to kind of continue the discussion offline. And all the listeners for today's webinar, if you're interested in collaborating or contributing to this effort, please do contact us. We'll try to see how we can incorporate your views and your opinions as a part of this. I think we are going to be running out of time. And I just wanted to acknowledge, I'm sorry I could not get to all the questions. We will try and summarize some of the questions, and we will see if we can send it out as answers by email later. I'm going to take a snapshot of the outstanding questions. So Agus, I really appreciate you taking time of your busy day and making time for us and sharing your amazing research and views about model risk management and also best practices in general. And even though we're not able to meet, I really enjoyed our conversation when we met in San Francisco early in the year. I wished I can go back to those days, or we'll look forward to again meeting in person and have those discussions around coffee tables, around dining tables to extend the thought, and that's where we all get energized, and we can share our thoughts and see how we can make this practice much more accessible for the people who are coming in new in the field, and it's also for sharing the best practices across in the industry so that we can make this a more formal and well-established best practice. With that, I thank you again, Agus. Do you have any last words you would like to say before we can adjourn for the session today?
No, thank you for the organizing this. It's really fun, Sri, always interacting with you. So looking forward to see you again very soon in the post-pandemic here. Otherwise, we'll see you in Zoom. So for the audience out there, if you have any question, let me know. And you have my LinkedIn contact as well. So we'll be happy and check some of the paper that my team produced that published in archive if you're interested in.
Thank you so much, Agus. And last announcement, the slides of today's presentation, I think there were a couple of requests, and also the video of today's presentation will be made available. And if you go to qusummerschool.splashthat.com, we are archiving all the links to all the summer school lectures. So you'll be able to access the lecture and also the slides there. With that, I would thank you again for attending this session. And I'll see you again next week to hear from Dr. Julia Fanti on synthetic data generation. Thank you very much.
Thank you.
Bye-bye.
Bye.